Hello and welcome to today's session. We're looking at nuclear physics and the discovery of the nucleus. We have three objectives today. First one, to describe the experimental setup used by Rutherford to probe the structure of the atom. Second is to explain how the results of this experiment provide evidence for the nuclear model of an atom. And the third one is to explain how an estimate for the nuclear radius can be obtained from Rutherford's experiment. So Ernest Rutherford, 1871 to 1937, learned physics in J.J. Thomson's lab, known for the scattering experiment for the alpha particles with gold foil. So you may have come across this at GCSE. So we just go into a little bit more detail around this scattering experiment and what it means for the nuclear model of the atom. So what happened in the scattering experiment? You have an alpha particle source, lead collimator to focus the beam of alpha particles, and they were fired at gold foil. So a very thin sample of gold foil. So according to Thomson model, the alpha particles would only be slightly deflected. So if you recall Thomson's plum pudding model, where you have the idea of it being a positive charge with currents of negative charge. But Rutherford discovered that they were deflected through large angles, and some were even reflected straight back to the source. And from the results of the experiment, we moved on to the nuclear model of the atom. We have a diagram here of Rutherford's setup. The beam of alpha particles, which are incident on the gold foil, and then you've got a circular zinc sulfide screen, so it will fluoresce when we have particles hitting it, so you can detect the various angles of deflection. So most of the particles pass straight through, but some were deflected back. Again, you'll see that diagram, what happened. So what he expected then, most of them to pass through like that, and we saw that we had some ricocheting and being reflected. So predicted result, some slight deflection. Observed result, we've got some very large deflections. So we have to interpret the deflections and what this means. So if most of the particles, the alpha particles, pass through the gold foil atoms, that suggests that the atom is mainly empty space. And then if you've got some deflections back, some very strong deflections, there's a small positive nucleus, because the alpha particles are positive and they're being deflected back. That was the main thing that you could get from this. So if we can show here what would happen with undeflected particles. And where they're deflected. So these dots here in the atom represent a small positive nucleus. So with this then, as I said, there's a small, heavy, positive particle. So that's what the idea was if you've got this deflection. And there's 4 cases that you can think about. Particle bouncing off the atom, if it goes through the atom, if it was attracted to the atom, and it's altered as it passes through. So we could think about that, what this would mean in these 4 scenarios, what would happen. So based off that, we come to a conclusion. So description of the alpha particles. If they don't diffract, then the alpha particle radiation is a stream of particles. So that's our hypothesis based on the observation. If the alpha rays deflect towards a negatively charged plate and away from a positively charged plate, that means our alpha particles have positive charge. And then if these alpha particles are deflected by very slightly by an electric field, so remember cathode is negatively charged. A cathode ray passing through the same field is deflected strongly. So they have either a much lower charge or a much greater mass than electrons. So based off those observations, you can make some hypotheses of the alpha particles. So we've got our plum pudding model, which was Thomson's original model. And based off Rutherford's experiment, the nuclear atom. So based off the alpha scattering results, there must be a small positive nucleus that is causing these deflections, as the majority of the alpha particles passed straight through the atom. So quite a lot of the questions you'll be asked around Rutherford's model is to compare the two. So you might get a question to describe Thomson's model and then the experimental results of Rutherford's model and the reason why we go for the nuclear model of the atom. So that will be the description question. So it might be 3 or 4 marks to describe the 2 models, or it might be just a question describing Rutherford's scattering experiment. Conclusions of Rutherford's scattering experiment then. Firing these alpha particles at a very thin gold foil, most of the alpha particles pass straight through. Some are deflected by a very large amount, and this was used to really formulate the idea that there's a small positively charged nucleus because the alpha particle is positively charged. Rutherford used the observations from this experiment to estimate the size of the nucleus. And the other point is that the electrons are floating around the nucleus, so they're around the nucleus. And as I said before, if you're going to take physics further, you would talk about the electrons being in sort of a probability distribution. So there's a probability of where they'll be around the nucleus, so we don't know where they are exactly. And that's what you need to look at. So in terms of Rutherford's experiment, those 3 points and the experimental setup as well. Sometimes you're actually asked to sketch the setup of the Rutherford scattering experiment. And we'll look at 2 methods of calculating the size of the nucleus. So 2 ways to sort of give a rough estimate of the upper limit of the size of the nucleus. Okay, so the first way of trying to estimate the size of the nucleus is to use the electrostatic energy formula. So you've got 2 charged particles, and then we've got RC as our distance of approach, because the particle is reflected. And what we'll do is look at that one first of all. So that is from the field section. So that's the first way of looking at the size, giving a rough estimate of the upper limit. So the equation from your formula sheet, electrostatic potential energy, 1 over 4 pi epsilon naught, Q1, Q2 over the separation. So RC is the separation between the alpha particle and the nucleus. If we put in some values, E naught is the permittivity of free space, as you see on your formula sheet. Q1, Q2, charge of the particles, as I said. So if we want to find RC, we need to make RC the subject. RC would be equal to Q1, Q2 over 4 pi epsilon naught times the energy. If we've got an alpha particle, it's a helium nucleus, so the charge on that is 2 times E. We know E is a charge on an electron, or the fundamental charge, 1.6 times 10 to the minus 19 coulombs. For gold nucleus, 79 protons in the gold nucleus, so we can have the charge of that, so 79 times that. And the energy, so 768 mega electron volts, that rest mass energy, and we can convert that into joules. So kinetic energy of these alpha particles. So by doing a calculation, if we assign an energy for it, so if we give it energy of 768 MeV, so typical energy of these alpha particles, so kinetic energy of the alpha particles, that includes the rest mass energy of the alpha particles. And E naught, again from the formula sheet. So putting those values into the equation, put it into a calculator, we get 2.96 times 10 to the minus 14 meters, which is a bit large, and we'll talk about why that is a bit large. We're treating this nucleus as a point charge, and it's not at this level. So when we're thinking about the nuclear physics, it's not a point charge at this particular level, and the alpha particles are stopped some distance away from the nucleus, so they don't get right to it. They're stopped some distance away because of the repulsion, so we can't consider it a point charge, and they're stopped a distance away from the nucleus, and we need higher energy alpha particles to penetrate the nucleus as well. So values for the nuclear radius given by other particles such as protons, neutrons, and electrons are slightly different. So that calculation was an upper limit. The other way, which gives a much better estimation, for the size of the nucleus will. So 1 in 10,000 particles are deflected by more than 90 degrees. We've got a very thin foil with n layers of atoms, so the probability of being deflected is about 1 in 10,000 n if there's n layers. And it's going to depend on the cross-section of the nucleus to the atom. So this is the other method of doing it. So we can express the cross-section of the nucleus over the atom if we think about the area, so pi r squared over pi r squared. So r, little r being the nucleus, big R being the atom. If we want to know about the diameter, obviously the diameter is equal to the radius, is twice the radius. So we can change the expression for pi r squared to pi d squared over 4 because it's d over 2 to give us our radius. This gives us an expression of 1 over 10,000 n, so d squared, little d squared is equal to big D squared over 10,000 n. So this method basically tells us that the size of the nucleus relative to the atom, if we give it an example, is like a football inside a football stadium. That's basically this second method. We'll look at another method as well further on in chapter 26, where we look at nuclear density. So there's another method as well. So you'll see a third method at this level where we can calculate the radius of the nucleus by looking at nuclear density. So that's another way. But for this part, the two methods so far, thinking about the electrostatic potential and then also the effective cross-section of the nucleus to the radius, and that's the two ways of doing it. Okay, so that brings us to the end of this session. Your task is to complete the 26.1 summary questions. So have a go at those summary questions. Obviously you need to prep for FA3, but still have a go at these summary questions. And then the exam style questions are on Learn Zone as well. So summary questions which need to be submitted, turn it in just to check your understanding, and then try the exam style questions as well. And as usual, if you've got any further questions, send me a message via Teams or email and I'll get back to you. Okay guys, take care. I'll see you on the next one.